Hi, my name is Christine Donnelly, and I'm going to present my final project for CS224D at Stanford University entitled A Multimodal Neural Network with Image Feature Attention for Image Caption Generation. So I'm going to do a brief video walkthrough of my poster, starting with the introduction and problem statement. So the problem that I'm looking at here is accurate image caption generation of sentence long length for arbitrary images. This is an important challenge in machine learning and computer vision. And there have been a number of publications looking at this challenge over the past 2 years. So in previous works, the majority of authors who are using neural networks to address this problem use a model which involves some variation on a recurrent neural network for caption generation and a convolutional neural network for image feature extraction. So typically the recurrent neural network is either preconditioned with the image feature vector at the first time step, or is reshown a static feature vector at each time step until sentence generation by the RNN is completed. But in one work by Kelvin Xu and his co-authors, an attention mechanism is used, whereby the recurrent neural network is shown a portion of the image feature information at each time step. And in my project, I also use an attention mechanism with a different algorithm for selecting the attended image region at each time step. I hypothesized that while an overall image summary vector can already lead to strong caption generation performance, the addition of the attention mechanism will help with fine-tuning of feature recognition and more accurate adjective descriptions of properties such as the color of image subfeatures, to avoid mistakes such as the ones shown in the baseline model where this bear is incorrectly labeled as being a white bear. So in this project, I use the Microsoft COCO dataset for training and evaluation. This is a dataset consisting of overall more than 130,000 images, each with 5 captions generated by volunteers. So in my work, I use 80,000 of these images for training and 10,000 for validation. And I use the remaining 30,000 images from the provided validation split for my final testing. This was because the server, which should evaluate performance on the additional 40,000 test images, is currently not functioning. So instead, I just split up the validation image split provided. In any case, so now I'll describe the model used in this project. So I'll start with a description of the baseline LSTM network, which is in this box. So this model uses a standard long short-term memory cell with the update equations for the forget gate, output gate, input gate, internal cell state, and finally the hidden state shown on the poster. So in generative mode, the hidden state is used to form a probability distribution over the vocabulary size to select the next input word. And then to incorporate image information, a feature vector from a convolutional neural network, in this case the 16-layer VGGNet, is also used. So the feature vector is 4096 dimensional and is taken from the last layer of the last fully connected layer of the convolutional neural network before the final projection and softmax classification. So that's this layer here. And so this feature vector is projected into the 200-dimensional word embedding space with the trained weight matrix and is used as the first input to the generative LSTM network at time step t equals 0. So next I'll describe the extension of this model to include an attention mechanism. Sorry. So now the LSTM cell has 3 inputs at each time step: the input word embedding, the hidden state from the last time step, and also an attended image feature vector, which I'm calling W. So all 3 inputs are used to compute the network gate, cell state, and the next hidden state. Like before, the hidden state is used to produce an output probability distribution for the next word. However, as shown here, the hidden state is also used for a second task. So the hidden state is used to produce a 512-dimensional feature selection mask. So note that for the VGGNet convolutional neural network used in this work, the last layer before pooling in the fully connected layers consists of a 14 by 14 grid over the image of 512-dimensional feature vectors, or 196 feature vectors total. So because the VGGNet uses ReLU nonlinearities, these vectors contain either zeros or positive values. The feature selection mask vector, output by the network, specifies which subtype of image features is most important for the network to see at the next time step. So the inner product of the mask vector is taken with each of the 196 spatially distinguished feature vectors, so that the ones yielding the highest values will have the highest activation for the feature subtype sought by the LSTM output. The results of these image vectors are used to form a softmax probability distribution over the 14 by 14 image grid. Finally, the weighted sum of the 196 feature vectors according to this probability distribution is used for the image input at the next LSTM time step. So the probability distribution, and then this is how the image feature vector for the next time step is formed. So in the attention mechanism used by Xu and his coworkers, the hidden state of the LSTM was used to directly form a probability distribution over the spatially distinguished image feature vectors. On the other hand, in this model, I'm instead experimenting with having the network output the subtype of image feature information that will be most useful, which indirectly corresponds to particular spatial locations. So because there isn't a direct mapping from the network mask vector output to an image spatial location, it isn't always the case that the activated regions of the image at a given time step correspond directly with the next word generated. However, it is typically observed that at initial time steps there tends to be a very strong activation of the main feature or object in the image, and also at time steps where color descriptors are generated, there is often a strong activation of the corresponding color regions of the image. So this is shown in some examples, which you probably got a chance to look at while I was talking. For example, a red truck parked in front of a building. At the time step where red is output, the network focuses on the red regions of the truck as well as this woman's red dress. And then a woman holding a colorful kite on the beach right before colorful is output. The attention is focused on, indeed, the colorful kite. Okay, so now for results. Here I just show a number of sample results, which I label either successful, like partially successful with some sort of understandable flaw, or kind of more definitely incorrect. So just going through some examples, close-up of a bunch of broccoli. This one correctly identified yellow fire hydrant in the snow. The tennis player. Here in the flawed results, there's indeed a woman and a man in a suit, and they're both talking on cell phones, but the woman is not wearing the suit. Here there's a TV on top of a chair, but the cat is not on top of the TV. And here, this looks like a hot dog, but it's actually like a sub sandwich. And then And the incorrect ones, this one correctly identified that there's a mirror with a reflection, but there's no man or bus in the image. This one mistakes a boy for a girl. And this one, a woman taking a picture of a cat. I guess the blow dryer was mistaken for a camera, and the hair was mistaken for a cat, but that was totally wrong. So then finally, in terms of quantitative results, the most commonly reported metrics in other publications are the BLUE scores and the Meteor score. So I also looked at those metrics for my model. So I looked at my best model, my baseline model, the previously published attention models that I mentioned, and then a model which just used a simple recurrent neural network with image feature input at only the initial time step. So my model doesn't quite meet the highest metrics reported for the BLUE 1 or Meteor score, but actually does do better than any other reported metrics for the BLUE 2, BLUE 3, and BLUE 4 scores. So I think there's still a lot of work that could be done to improve these scores and create better, maybe more verbose and specific captions. But yeah, okay, that concludes my presentation of this work, and thank you for listening. Goodbye.